we have been studying about refraction, and as far as the last segment was concerned, we understood how to find the image location for refraction due to spherical surfaces. And that formula or that relation essentially was mu2 upon v minus mu1 upon u equals to mu2 minus mu1 upon r, where mu2 is the refractive index of the second medium, mu1 is the refractive index of the first medium. By first and second, what I mean is, let's say this is your interface, a spherical interface, and this is my medium 2, this is my medium 1, and both these media essentially are having different refractive indices. This has mu2 and this has mu1, and my light is coming from this side. Object would definitely be on this side, so u is on the left side and v is on the right side. If we take into consideration the correct sign convention, this formula would give me the image location in all the cases. Rather, this is valid for every kind of spherical surface. This is a convex on the first and concave on the second. Even if it was the other way around, concave on the first and convex on the second, the formula would have been valid because I have used my proper sign conventions. Now, naturally, you could got a hint that I could have created a sort of third medium, rather not a third medium, but a medium which is inside a bigger medium. What I mean by this is, let's say I create something like this. This surface over here, inside of this is an enclosure, right? And this enclosure is having a refractive index of mu2, and it is in the vicinity, or rather it's in a region or a space of refractive index mu1. So this side would also have mu1 and this side also mu1. The idea here is, the shape is not important. I could have also made it like this. Mu2, this is mu1, this is mu1, or could a combination of it. This is convex here, convex this side too. This is concave here too. I could have made convex on the one side, concave on the other side too. So this is not important, relevant for our current discussion. You'll understand it just right now. What you have to understand is, I have two interfaces. This is interface number A, this is interface number B. Similarly, interface number A, interface number B. So my refraction would happen at both these interfaces. And I can make a very simplifying assumption that this is a very thin enclosure. If I say this is a very thin enclosure, all the measurements which I was essentially taking from this point over here for one curved surface can be thought of as this point for this surface, this point for this surface, and the center of the enclosure. All these points essentially are the same point. Not the same point in true sense, but in approximation, they are the same point because the lens is thin, the enclosure is thin. See, I've used the term now lens suddenly. This enclosure is also known as lens. What I mean by lens now is, if you have a medium inside a medium and that medium is having a different refractive index than the region around it, then that becomes a lens. See, this is a very abstract kind of a definition, but I personally prefer this definition. So if you have a medium, a very thin medium, trapped or inside a large space of a different refractive index medium, then you have a lens. This lens could take any shape, that doesn't matter, but this lens can only be studied by us if both the surfaces are of spherical nature, concave or convex on either sides, that doesn't matter, but they should have a spherical nature. Now, the advantage I have with spherical nature is I can apply my refraction formula at this A interface and at this B interface. Let's try to apply that. When you apply at interface A, what will happen? My object distance could be thought of as just u, and that would create an intermediate image. Why intermediate? Because after refraction from here, the ray doesn't stop refracting, it refracts here too. So I'll have a second image formation by this B interface. That would give me the final image. So let's use the intermediate image thing as intermediate image location is, let's say, some V1. So at interface A, what will happen is, this is my refractive index of second medium. So mu2 by V1 minus mu1 upon u would give you mu2 minus mu1 upon R1. Why R1? Because interface A could have a different radius than interface B. So let's just say that interface A has R1 radius of curvature and interface B has R2 as the radius of curvature. So they could have different radius of curvatures. Now this is for interface A. Similarly, I can do a similar analysis for interface B. So at interface B, just do the same kind of a thing. This V1 over here would act as your object, and this thing would provide you a final image at V location. But this thing is your second medium and this is the first. So I'll have to use mu1 upon final image location minus mu2 upon my intermediate image, or rather the object for the second interface, B interface, that is V1. This is equal to this minus this in terms of refractive indices. So mu1 minus mu2 upon R2. Now if you observe these two relations, you could also term them as relation number 1 and relation number 2. By adding them, you can simply say that these two terms would be cancelled away. So by adding 1 and 2, what's the advantage of that? I don't need V1, that's an intermediate thing, I need the final thing. So by adding 1 and 2, we get these two things go away. Just cancel them out from here itself. What you'll be left with is simply mu1 by V minus mu1 by U. I can take mu1 common. Mu1 1 by V minus 1 by U is equal to, now if you add this and this, here you have mu2 minus mu1, here you have mu1 minus mu2. If I just invert it through, what I will get is minus of mu2 minus mu1, right? And I can take mu2 minus mu1 as common. I'll not tax you on your intellect right now, I'll just do it for you so as you understand. Mu2 minus mu1 upon R1. Now invert it through. What you will get is minus of mu2 minus mu1 upon R2. On further simplification, what you would get is equal to, take these two things as common and divide it with mu1, you'll be left out with mu2 upon mu1 minus 1 into 1 by r1 minus 1 by r2 inside the brackets. Now if you observe this carefully, this is giving you the final image location if the object location is known. And this thing over here is also known as lens formula. This is your lens formula. Now, let's say you have kept your object at infinity. The idea of object at infinity is parallel rays are coming towards the lens, either this or this. And by the definition of lens, what you have to understand is parallel rays, if the lens are converging, they have to converge at focus. And if the lens are diverging, they should appear to start from focus. So when I say converging or diverging, what I mean is my image should be formed at focus if my rays are parallel. If my object is at infinity, my image should be at focus. So if you put u equal to minus infinity, why minus infinity? Because obviously it put it left on the left hand side of your measurement point, right? So if u equal to minus infinity, this thing goes to 0. So 1 by v is equal to this thing over here. And as far as my definition of focus is concerned, my image should be formed at focus. So 1 by v should return you 1 by f, which means this thing has went away. This guy, big huge expression, is essentially 1 by f because v is equal to f. So 1 by v is equal to 1 by f. So I can write over here that 1 by f of a lens is equal to mu2 upon mu1 minus 1. I've just copied this thing down here by 1 by r1 and this thing is known as lens maker's formula. This is your lens maker's formula. Why such a name? Reason being, this formula can be analyzed to understand how focal length depends on 2-3 things: refractive indices and radii of curvatures of both the surfaces. If f comes out to be positive from this lens maker's formula, it means there is a converging type of a lens. Why? Because parallel rays are actually meeting at a point. That's why f is positive. If parallel rays are actually meeting, it could happen in this situation or this situation. Geometry is not important. That's what the idea of this equation is. Geometry is not important. It's a combination of geometry and refractive indices. So if parallel rays actually meet, that's converging. So focal length has to be positive. If parallel rays diverge, they don't meet, they appear to come from some point, that would be negative, of course. So f negative means diverging lens. Geometry is not important. Even this could be a diverging lens or this could be a converging lens. Geometry is never important. It's geometry plus refractive indices. Now I can further say, I can combine these two lens formula and lens maker's formula and make a hybrid lens formula. And that hybrid lens formula would be, simply 1 by v minus 1 by u is equal to 1 by f. this would be more followed by you in the course of numerical calculations, which essentially is the same thing. This guy over here gives you the focal length, lens maker's formula, and I've used this thing to give me a simpler lens formula. 1 by v minus 1 by u is equal to 1 by f. Usually this is used in your basic classes or your elementary classes, foundation classes. So generally you will be using this formula, and this formula interchangeably depending on situations, what suits you, and keep this thing always handy because it's easier to remember this. But the moment you remember this thing should click here, and if it clicks over here, this thing is also unlocked. Now I briefly talked about converging and diverging lens, and I said that this is independent of the geometry, by which I also meant that if positive means a converging lens and f negative means a diverging lens. See, I tend to write my R either in this way or this way. Don't be bothered by that. That's a very rudimentary thing. So f negative is a diverging lens thing and f positive is a converging lens thing. Now if you look at this situation over here, this thing over here has to be positive for a biconvex lens. What is biconvex lens? This diagram over here is a biconvex lens. Why? Convex on this side, convex on this side. 1 by R1. R1 is towards this side, so positive. R2 is negative. But there's a negative term in between two. So positive minus a negative. Positive plus positive. So this guy is positive for a biconvex lens. All depends on this. If this thing is positive, your focal length will be positive. So biconvex would be converging if this is positive, right? If mu2 by mu1 is greater than 1, this is positive. This means if mu2 is greater than mu1, your biconverging lens is biconvex lens is converging lens. Just write it over here. If mu2 is greater than mu1, biconvex lens is converging. And if mu2 is less than mu1, your biconvex lens is diverging, which is this thing. Now I can further say it for biconcave lens, convexo-concave lens, or a concavo-convex lens, but those things doesn't make sense. It becomes repetitive after some point of time. So I won't go into the details of it. Just understand that I have to use this lens maker's formula to find out f is positive or negative. When f is positive, you have a converging lens, and when f is negative, you have a diverging lens, and the geometry is independent of it. And just for the sake of example, a biconvex lens would be a converging lens only under the situation when your mu2, the lens material refractive index, is greater than the refractive index of the medium in which it is. And when the refractive index of the material of the lens is lesser than the medium refractive index, then the biconvex lens is a diverging type lens. Now let's now understand all these things has been done for point size images. Now till now we have been talking about point objects and image formation for point objects. These formulae have been derived for that situation. But let's say you have an extended object. So I should have a magnification relation, as we have done for our mirrors and for a refracting interface too. So for lens also I'll do a similar treatment. I'll do with a particular situation, and other situations have a similar treatment and it becomes very monotonous. So I would just leave it to you as an exercise to verify that if it comes the same or not. Let's draw a situation. I could have just said a lens here, but just for clarity purpose I'm drawing a biconvex lens. It doesn't mean that I need a biconvex lens over here. I could have had like anything over here. This is the principal axis. This thing over here is your object. So an image would be formed something like this. This is one ray which is traveling without refraction, and other ray could be like this without refraction. So this would, if this is your A and this is your B, this could be B dash and this could be A dash, and this thing over here is your O. O is also known as optical center, and essentially this is a thin lens, right? Just always remember that whatever I'm doing is for a thin lens. So in a thin lens, this point, and this point all are same. Just mention O, optical center. O is your optical center. Doesn't make much of a difference mathematically speaking, but yeah, you should know the terminologies. Now, if you look at this diagram, triangle ABO and triangle A''B''O are similar because this angle is equal to this angle, and this is 90 degree, this is 90 degree, which means these two triangles are similar. So I can say that A''B' by AB is equal to OB dash upon OB. Now let's come to the exact specifics over here. Magnification is defined as height of image upon height of object. In this situation, the image is forming on the bottom side, right? So HI would be negative. So I'll have a minus with A''B' because A''B' thing or A prime B prime thing is giving you a positive. This is a positive, this is a measurement, but a negative sign is for the sign convention upon AB. If I plug in this thing for A''B' upon AB, this thing comes over here. So magnification now becomes minus of OB dash or OB prime upon OB. What exactly is OB prime? OB prime is positive V. Just write it over here. I'll just write it for you. This is minus OB prime on OB. OB prime is your positive V, and OB is your minus U. Why minus U? Because obviously my object is in the left side, so U would be negative, but this thing over here is OB is positive, so minus U. Minus and minus becomes plus. This is V by U. So magnification for a lens HI upon HO, height of the image by height of the object, is equal to simply V upon U, right? This essentially is very similar to other situations too of mirror and curved surfaces, but it has a slight difference, but the treatment is similar. You always have to do HI upon HO. I hope this kind of completes the whole discussion on this lens, and we'll gradually move on to more specific situations of lens, but as of now it's kind of okay.